Hello everyone, my name is Pedram Zaree, and today I'll be presenting our paper titled "That Doesn't Go There: Attacks on Shared State in Multi-User Augmented Reality Applications." Before I dive into the details, I want to thank all of the authors because of their hard work, Slocum and Yicheng, who led the project, Erfan, Shayegani, Professor Nael, Abu-Ghazaleh, and Professor Jiasi, Chen. Nowadays, a growing number of AR applications facilitate the multi-user interactions with the shared holograms. And you can see some of the examples here. And these applications are supported by major industry players. For example, the AR core framework is provided by the Google company, is one of them. To create a shared AR experience, the user can use the AR devices to sense and scan the real world and store the information in a shared space. And then the other user can sense the same environment to access the information in the shared space. And this mechanism makes these systems vulnerable to the attacks. In the following parts, I'm going to talk about the shared state in the augmented reality, the threat model, the attacks we explored in the paper, and the proposed mitigation against the attack. Actually, to view the holograms, the AR devices need to write some information into the shared state and read from it. For example, in the left video, you can see that AR device is scanning the environment to write a hologram into the shared state. And then the other user can scan the same environment to access the hologram in the shared state. And the question here is that what happens if an attacker poisons the shared state? And what's the shared state? It's a collective set of information necessary for enabling interactive and consistent experience among multiple users. And it contains some information. First of all, it contains the visual feature map of the real world, and we call it the point cloud map. And the next type of information is holograms. And the clients can have the write and read operations to communicate with the shared state. And for these operations, they need the key value pairs. The key is the real-world environment features. It can be the point cloud, the visual features of the environment, or IMU data or GPS of the location. And the value is the hologram stored in the shared state. For example, the Google AR Core framework provided these operations, the host cloud anchor for writing into the shared state and the result cloud anchor for reading from it. For example, here, Alice is a user and acts as a reader. She provides the key information, which are the, for example, information of the environment to get access to the shared state. And then she can, fetch the hologram from the shared state. Or the other user, Bob is a writer here, provide the key information and get access to the shared state and can write some information into it and update the point cloud map and the hologram here. We have examined the commercial multi-user AR frameworks and we classify them as you can see in the table. For example, we can classify them based on that the shared state is local or global. The local case is used in the small local areas like the indoor rooms. For example, the Google AR Core framework is one of the examples. And the global case is used in the outdoor locations and world scale. For example, the Pokemon Go game is one of the examples, or the Geospatial API by the Google, or Map Layer by the Meta. And here in the global case, one of the features and keys is the GPS of the environment. Or we can classify the shared state based on they are curated or non-curated. In the curated case, only the curator can write into the shared state, but the non-curators can read from it. For example, one of the examples is the augmented art gallery, where just the curator can write into the shared state. And in the non-curated case, all of the users can write into the shared state and read from it. For example, the on-the-fly game is one of these examples. And about this threat model, an attacker participates in a multi-user AR applications, uses an unmodified AR application to access the shared state. And as a regular user, there is no special permissions for the attacker. For example, in the read attack, a victim user writes information into the space. It can be sensitive information, and the attacker can read this sensitive information. And for the write attack, you have the same process, but here, first of all, the attacker injects some malicious data into the shared state. And then the victim user reads this information from the shared state. We had 3 scenarios for the attack in the paper, and we explored. The first one is a local non-curated case where the platform we explored was Google Cloud Anchor API. Here, the attacker can write into the shared state or read from it. In the next scenario, which is global and curated, the platform is the Google's geospatial API, and here, attacker just can only read. And the last one, which is global and non-curated, the platform was a mapillary by Meta, and here again, attacker can write or read. For the first scenario, we have 2 types of attacks. The first one is a remote read attack, where the attacker wants to remotely read some information. Here, the attacker has control of their own device. First of all, the victim user shows the normal input to the camera. The normal input is here is a real environment and location. And it stores a hologram into the shared state. But then the attacker can show the adversarial input to the camera. And here the adversarial input is a photograph of the location and environment. And can have access to the hologram of the shared state. And the next type of attack is the remote write attack. Here, attacker can show the adversarial input to the camera. Here again, the adversarial input is the photograph of the location, which is on a screen, and write the hologram into the shared state. And then when user show the normal input to the camera, it can fetch a hologram from the shared state. And for the evaluations, we explored 6 different environments. 3 of them were indoor locations, and the rest of them were outdoor. And the device we used was Galaxy S20 Android phone. And we had good and robust success rate among the attacks. For example, this table shows you the attack success rate for the remote write attack. Or this graph shows the effect of distance on the remote read attack. Distance here is the distance of the attacker's device from the monitor and for the picture of the environment. And the best results were at a distance of 1 meter. In the next scenario, here attacker just can read from the shared state, and attacker wants remotely read the hologram from the shared state. To do that, attacker deceives the Google's geospatial API by providing the fake camera input, which is the photograph of the location, and at the same time, fake GPS information. And it can be done with using the GPS spoofing applications. For example, here, in a real environment, the victim user could write a hologram to the shared state, but then the attacker can provide the fake GPS information and fake input camera and access to the stored hologram. For this scenario, we evaluated for 23 holograms and in different locations of the UCR campus. We used the Galaxy S8 and Galaxy S21 devices, and we had good and robust success rate through all of the locations. Again, this figure shows the effect of distance on the success rate. Distance is the distance of the attacker from the monitor and photograph. And in the last scenario, the attacker tries to inject malicious input to the shared state and change the point cloud map. And this is the point cloud generation algorithm. And it can be done by providing fake GPS input For example, in one of the scenarios, the attacker tries to swap GPS coordinates of 2 image sequences by editing image metadata. It's good to mention that the experiments done in a mapillary sandbox with permission and no public users were affected in these experiments. For example, here you can see that we had 2 image sequences and the attacker tried to swap the GPS informations. So finally, the image sequences were swapped in the mapillary. Or here is another example on the mapillary. You can see here 2 real environments with 2 signs here without any attack. But with the attack, we could swap the annotations here. And in the right side, you can see that we could swap the signs here, and it's a really dangerous scenario because now the annotation here is D is safe, but it's not safe actually. And the question is that how can we detect the fake camera inputs and mitigate the attacks? One idea is using additional sensor modalities, for example, using the AR devices equipped with the depth sensor. For example, here in the left image, you can see the output of the RGB camera, but the right side shows the output of the depth camera. And for evaluating these events, we use a learning-based method. We use a ResNet AD model to train it and classify the images, whether they are from the real location or they are a spoof image. And for collecting data set, we collected images from 15 real scenes, and in each location, we collected 300 pairs of color and depth images. And we did the same process to collect images in front of the monitor to provide the spoof images. And we use 80% of the data for training, and we tested on the rest of them. And finally, we could detect the spoof images with the precision of about 84%. Also, there are potential mitigations, and for more information, you can read the paper and get more information about them. And in summary, the AR devices sense information about the common reality, and these informations shared across applications and systems and provide the attack opportunities for the attacker. We covered the 3 scenarios attack against the AR frameworks, and we proposed a mitigation against them. And for more information, you can scan the QR code to access the paper and the demo defense. Thank you so much.